Welcome back, my sweet little sacrificial lambs. Today we're going to just go over solving some problems. We're going to look at a couple that I think are maybe a little more challenging than just read the question, plug in numbers, turn math crank. You know what I mean? We're going to have to actually think about some of these. The challenging part is setting it up, and then the challenging part is also doing a little bit of math. So physics problems can get very difficult. I did write one on here that I was like, you know what, that one's maybe too hard, and I took it off. So they can get really out of control really quick. But oh well, that's life, you know. So we're going to just look at a few problems. We're going to talk about some skills that we went over earlier in the class and maybe forgot. And then you'll have a few problems to practice. So let's dive into them. All right, so let's start with this solving algebraically. This is one that likes to show up on the AP test. A lot of times they'll use words like, oh gosh. They won't say oh gosh, but they'll, be frustrated their pen doesn't work. They'll use words like derive. That's not a P, that's a D. Derive. Is that how you spell derive? Let me try one more time. Derive. They might say words like, I guess they might say solve. But they'll say, like, in terms of, and then they'll give you a bunch of variables and stuff. So I think usually derive is how they're going to say it. But so the question is, a mass is dropped from a building of height h. So we don't really care what the height of the building is, right? It's some height. It could be 15 feet. It could be 50 feet. We don't really care. And then lands with a velocity v, right? So I drop it from somewhere, and it lands going some speed. We don't know what they are, and we're going to see that we don't really care. We can solve the problem without needing specific numbers, but a lot of times that makes students uncomfortable. How high would the building need to be for the velocity at the bottom to double? Okay, so let's maybe draw a picture first. So we have a building here, maybe some windows on it, maybe like a little door on the front. There we go. And we're standing here. We're going to drop a ball or something off, and then this ball is going to fall down, and it's going to hit the ground, and it's going to have some final velocity, capital V. The height of this building is capital H. So when I drop at a height h, it's going a speed v. We want to know, what height building do I need to drop it off of to get to go twice as fast? Okay, that's a fair question. I think a lot of students will intuitively say one that's 2h tall. Well, let's double the height. That'll double the velocity. But you can't just guess that. You kind of have to prove it. So let's talk about how we're going to go about doing that. So let's look at some equations. We are looking for how high. Height is usually a distance. So let's maybe look at our displacement formula. Let's write it down just so we have it handy. Okay. And we need the speed to be 2v. And in the way I've set this up, this is final speed. So we might need to look at some final velocities too. So let's write down our velocity equation just in case for that one too. All right. So let's look at this. All right. We want v final to be twice as fast. Because it says dropped, we're going to assume, and this is a pretty safe assumption, this is like physics code 4, v initial equals 0. Okay, so let's make some simplifications to our equations before we get too much farther. So v initial goes away. V initial times t goes away because 0 times t is 0. Okay, so that makes these equations look a little bit more friendly and accessible to us. Okay, so what we're looking for here is twice as much v final. So what we're going to do is we're going to plug in some numbers that we know just to get started. Because right now this looks like a mess, right? We don't know any real numbers. We don't know any times. We don't know any accelerations. We don't know any velocities. We barely have an idea of height. So let's go ahead and plug these numbers in and see what we get. So we'll plug in our final velocity of capital V equals whatever the acceleration is. We're probably in free fall, so we could probably say it's 10, but maybe we're not even on Earth, right? We don't know we're on Earth. So we'll just leave it as a times t. And we know that when the ball hits the ground, if we're saying the ground is 0 and this height here is h, we know that final displacement will be 0. Okay. We also know that initial displacement will be h. So we need to somehow relate this velocity with this height. They're in two different equations, so we're going to need to plug one into the other. So how can we do that? What variable connects these? Well, acceleration is in both of them, but that's probably a constant. That's a number, right? We don't really have a bunch of control over that. We do have t, though, connecting them. So how about we solve our velocity equation for t, and then we'll plug that into this. All right, try that. So if I solve this for t, we're going to divide by a, divide by a. So t equals the final velocity I'm looking for divided by a. Not too bad. Now we can plug this into our time and we'll see what happens. Let's switch to blue. Okay, I'm going to plug in some simplifications here. 0 equals h plus 1/2 a times, that should be a capital V. 1/2 a times v over a squared. Okay. And now we're looking for this height, right? Apologies. I haven't worked this out ahead of time, so you're kind of watching me discover it on the way, which is fun. So let's maybe do some simplification here, see if we can't. So we have 0 equals h plus 1/2 a. The way this squared works is v over a times v over a. So you're just going to distribute the two in. So we're going to have v squared over a squared. And then this a can cancel one of these a's. So we have 0 equals h. And then we have plus v squared on top. And then we have 2a on the bottom. All right. So let's go ahead and just move this thing over, and we'll get an expression for h. So h equals negative v squared over 2a. And you're going to say, what, Barton, you've lost me. This is too much. Okay, that's really kind of normal at this point. All we really want is height as a function of that velocity we're looking for, okay? You want to put the velocity and the height in the same equation. You want to isolate one of them. Because we're looking for the height, how high, let's get the height by itself. Okay, now you're going to say, how do I use this information to figure out how the height has to compare? Okay, glad you asked. What we're going to do now is we're going to change the v. How, you might ask? How high would the building need to be if the velocity at the bottom needs to double? So we're going to take the expression we have relating the height to the velocity, and we're going to replace velocity with 2 velocity. And then we're going to simplify and compare the two equations. So we could call this, if you want, we could call this height 1. And then we'll plug this in, and then we'll call that new height 2, shall we? So height 2 equals, bear with me here, negative, where the v is, we're going to put parentheses and replace it with 2v squared over 2a. Okay, let's simplify and clean this up a little bit. This is negative 2v squared would be 4v over 2a, and then 4 over 2 can be reduced to 2. All right, so here is the height that we need to be at to get double the velocity. Here's the height that we need to be at to get the velocity. Now what we're going to do is we're going to set up a ratio of them to see how much bigger is this height than that height. So let's put h2 on top. It really doesn't matter which one's on top, but usually you want the final on top. So we'll put h2 on top. h2 over h1. Okay. This ratio will tell us how much bigger one is than the other. And you'll see what I mean at the end. Well, what does h2 equal? h2 equals negative 2v over a. And then what does h1 equal? It equals negative v. Oh, sorry, this v should be squared. Pardon me. Squared. There we go. Squared. Negative v squared over 2a. And now we have to simplify this fraction. All right. When you're dividing a fraction by a fraction, we flip and multiply instead. So we're going to have negative 2 v squared over a times negative v squared, oops, sorry, flip. I forgot to do the flipping part. 2a over v squared. Now we simplify. So the v squared cancels the v squared, the a cancels the a, the negative should still be there. And then negative 2 times 2 over negative 1 is negative 4 over negative 1, which is 4. Okay, we might even want to leave it as 4 over 1. What this is telling us is that h2, the new height, is 4 times h1, the original height. So how tall does our new building need to be? Our intuition said, well, if I want to double the velocity, probably just double the height. Not the case. This height needs to be 4 times the original height. Okay. So let's go over that maybe just one more time real slow. Let's take a step back, look at what we did. Okay. We started with writing down the two equations we know that relate to the variables we're interested in. Velocity and how high would be a displacement or a position. Okay. We read the problem. We found some variables and plugged them in to simplify our equations. The v naught here goes away. The v naught t here goes away. Then we said we want to solve for the thing we're interested in, the height, so that it's equal to the other variable in some way. The way we did that was we took this equation, found the connecting variable, t to t, isolated the t, then plugged this into t in the other equation. Okay. Once we had that, then we took this equation, we replaced the variable with the new value, we simplified it, and then we set up a ratio of the two equations, simplified, and then that gave us a ratio of the two heights. Okay. I promise it won't be that hard when I give you a problem on your homework. I mean, it's okay. It can be this hard, but I'm going to try not to give you one this hard. I feel like this is maybe a little harder than I thought it was going to be, but that's all right. It'll put hair on your butt. All right. Let's go look at some other problems. Keep in mind that these are solving challenging problems, not solving easy baby problems. Okay. So here we are talking about two accelerating objects. Two objects are dropped 1 second apart from each other. The mass of each is unknown. So we could have like a small mass and a big mass, or we could have like two big masses, or we could have a big old nose and then like a frowny face because physics is cool. But either way, it doesn't matter. What will happen to the distance between them? Okay. So here are our options. I wish I could put A, B, C, but it wasn't letting me. The only way I could do is numbers. So the things that could happen, okay, it's always nice in physics to, before you do the problem, have a guess of what the answer might be in your head. That way you have at least some direction. So what could happen to the distance between these two objects? So I drop one, it starts to fall. Then I drop the other one, and then they both start to fall. Okay. Well, the distance could increase. This one could drop, and then it drops way farther, and then this one drops a little. And then this one drops way farther, and then this one drops a little more. And the distance between them continues to increase. Okay. The distance could decrease to 0, right? They could get closer together. This one could fall, and then I drop this one 1 second later. It falls, it falls. It falls, it falls, it falls, it catches up a little, and eventually they'll be right next to each other. That could happen, maybe, I don't know. They could stay the same distance apart forever. This one could fall, and then they just do this and fall in unison together forever. Or another possibility is that we don't have enough information to tell here. So there are a lot of different approaches to doing this problem, and I don't think any of them are incredibly straightforward. So let's look at a graphic approach, and then let's maybe look at an equation approach. Okay. A lot of times what you want to do is maybe even make up easy numbers to plug in. Because they're not giving us any numbers, you can sort of plug in your own test numbers and then just go back and think, well, would these test numbers give me any weird answers? A lot of times if you pick 1 or 0, you might get weird answers just because you could multiply by 1 and then it looks like they stay the same. But if you picked any other number, they're definitely going to change, right? Or you could be adding 0. So that's maybe not good. So we have two objects that are dropped 1 second apart. So let's talk about the dropping part. If I'm dropping something, we already talked about v naught being 0. Okay, so the initial velocity for the first one, we'll call this one, this 2, would be 0. And the initial velocity for 2 would also be 0. Okay. If I'm dropping something, and it doesn't say anything about air resistance or parachutes, we're probably assuming no air resistance. Okay. So this sounds like a free fall problem to me. So let's set it up like a free fall problem. Okay, so if it's in free fall, we get a couple of things. We get the acceleration is 10 meters per second squared downwards. And we'll set that for both of them. And we'll make them negative just because I like down to be negative. But it's up to you. Okay. We also know that they are starting from the same position. Okay, so x naught 1 equals 0, x naught 2 equals 0. Okay, so we have some information here, even though this problem looks like we don't have very much. Another important thing, it says the mass of each is unknown. This property of free fall does not depend on mass. Bowling balls and feathers fall with the same acceleration as long as they're in vacuum. So we're going to assume that this mass is maybe not super duper important. We'll come back and talk about it, but let's just go with what we have. Okay. So let's do a graphic approach. Okay. So let me get a ruler, actually, because the distance is definitely going to be important here. Okay, there's our ruler. Set them both at 0. There's 0. Oops. Okay. All right. So 1 second goes by, and we've dropped this ball. It starts with the initial velocity of 0. Let's go ahead and just calculate the first one. Let's maybe do some calculations for this one, and then we'll graph its position as a function of time. We'll do a motion map. So x final, or the position we're at, equals x initial, which is 0, cool, plus v naught times time, initial velocity is 0, cool, plus 1/2 at squared. Okay, a is -10, so 1/2 times -10, that's -5. So our final position equals -5 times time squared. Okay. Let's go ahead and just make each of these 5. So there's 5, 10, 15, 15, 20, and so on. So if I plug in 1 for t, 1 squared is 1, times 5 is 5. So this ball will fall, this ball will fall 5 meters. There's our first one. Actually, let's make these infinite cloners. How cool would that be? Okay. How do I do that? Where is it? Infinite cloner. There we go. Watch this. After the first second, there's the first ball. Okay. Let's plug in like 2 or 3 more times to look at a motion map of this. If I plug in 2 here, 2 squared is 4. 4 times -5 is -20. Let's lock this down before I move it a third time. Okay. So we're at -20 now. Okay. And let's do 3. 3 squared is 9. 9 times -5 is -45. So 25, 30, 35, 40, 45. And then from there, it starts to get a little out of control. But this might be enough information to get us where we want. So our last one is going to be at 45. Okay, what's important now is that all this information for the second ball is exactly the same as this ball, right? It still starts at 0 velocity, still starts at position 0, but it starts 1 second later. So 1 second has passed. This ball has fallen 5 meters. This ball is still at the start. The second passes. This ball falls 10 more meters. This one begins to fall, and plug in 1 because it's fallen for 1 second. It goes to 5. Okay. Now, the third second passes. This ball falls another 25 meters. This ball continues on and is now at 20 meters. Then another passes. This ball would fall, what's 4 squared would be 16, times -5 would be -80. So this would be down here at where 16 is. Let's grab one more ball, shall we? Okay, and you can see it already doesn't fit on our screen. So there's that ball, and then this ball falls one more time, and it's here. Let's start comparing the distances between them. So this ball is 1 second in. At 1 second, this one is still at 0. So these are 5 meters apart. Another second passes. This ball falls to 20. This ball falls to 5. These are now 15 meters apart. Okay. This ball falls to 45. This ball falls to 20. Now they're 25 meters apart. And then you can see a pattern here. 5, 15, 25. The next one will be 80 to 45. This is 35. Next one will be 45, then 55. So we don't really have an equation to do this, right? We don't have a way to include this 1 second delay. But if we draw a picture, it becomes really easy for us to visualize and compare their positions. So what's happening to this distance between them? It will increase. Okay, cool. So sometimes you can't just brute force it with algebra the way we can here. And this is brute forcing with algebra. You know what I mean? This is algebra as flip. This one, not so much. This one, we drew a pretty picture. We inferred some information, and then we compared. Okay. Let's look at one more. This one is just being aware of how to set up some algebra and then being diligent with our assigning of signs and defining things. So we have two cars that start on opposite ends of a football field and are 100 yards apart, because America. One car travels at 15 yards per second, and the other one starts from rest and accelerates at 6 yards per second squared. Where will they be when they meet? So let's maybe draw a little doodle, because as we saw, sometimes pictures are helpful. So we have a football field. This is 100 yards apart. We have a car here, and we have a car here. And the idea is one of them is going to drive that way, the other is going to drive towards it, and we want to know where do they meet in the middle. One of them is going 15 yards per second, constant velocity. The other one is accelerating, but starts from rest or 0. It doesn't tell us which one is on which end. It doesn't tell us their masses. It doesn't tell, it leaves out a lot of stuff. So let's go ahead and pick. Okay. Here's what I'm going to do. I'm going to say this is the accelerating car. And this is the constant V car. I'll explain why I picked that once we get into the algebra, but trust me, I think it'll be a little easier this way. Feel free to do it the other way. Really, the difference is perspective, correct? One way, we're standing here. Here's our haircut. And we're looking that way at the field. The other direction, if I put this car on the left and this car on the right, would be if I were standing here looking this way at the field. So it's which side of the field are you standing on for which one's on the left and which one's on the right. Really, it's relative. It doesn't matter that much, so we'll just pick. Okay. I'm also going to say that the accelerating car, this I'll make initial position equals 0, and this one will make initial position equals 100. So right now, all I'm doing is defining my problem. I'm saying which side of the field am I standing on? I'm saying where am I saying 0 is at? Where am I saying 100 is at? And because this is positive 100, we're saying the positive direction is to the right and the negative direction is to the left. So we're defining our problem. We're setting up directions and axes and origins. Okay, let's go ahead and try and write some equations for these two cars. We're looking for where will they be. Where will they be is asking about position. So let's look at our position equations. For this car, x final equals 1/2 at squared plus v naught t plus x naught. So we can see x naught is 0. This goes away. Starts from rest for the accelerating car. So v naught equals 0. So this is 0 and goes away. And we're accelerating at 6 yards per second in the positive direction. So a is going to be positive 6. So our equation for the accelerating car is x final equals 1/2 times 6 times t squared, which is 3t squared. All right. Now let's write our equation for the constant velocity car. X final still equals 1/2 at squared plus v naught t plus x naught. Now it's constant velocity, so acceleration is 0. This term goes away. Its velocity is 15 yards per second, but it's traveling in the negative direction. So we're going to plug in negative 15 for velocity. And x, it's starting at 100 yards, so x naught will be 100. So let's simplify this and set it up. X final here equals negative 15t plus 100. Cool. Now, how are we going to solve this? We have two different equations. We could graph it, right? We could plug in 1 second. Okay, 1 squared is 1 times 3 is 3, so it'll go 3 yards. 1 times negative 15 is negative 15, plus 100 is 85. And then we could mark off their positions on the field and do it graphically the way we did here. But let's go ahead and just solve it outright, because I have a feeling because of 3 is a real nasty number. It's probably not going to be on a nice place. It's not going to be at like the 50-yard line. So when we say, when will they meet? If they are meeting, then this, oh no, my whole field moved. Then this car and this car must be in the same position. Same position means x final for this car equals x final for this car. So what we want to do is set our two equations equal to each other. Then, but then my x final will go away. Okay, well, we'll find time and then we can plug it back in, like in an algebra problem. So we're going to have 3t squared equals negative 15t plus 100. Now we're going to move everything to one side so it equals 0. So we'll add the 15t over and subtract 100. So we have 3t squared plus 15t minus 100 equals 0. And now this thing is a quadratic. Ah, how interesting. Okay, so to solve this, unfortunately, there's not a nice way. There's not a good physics trick I can teach you. We're just going to beat this thing to death with the quadratic formula. So A is 3, B is 15, C is negative 100. The quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And we're going to plug our numbers in. So we're going to have x equals, in this case it's not x, it's actually t. Let's use physics variables. T equals negative 15 plus or minus the square root of 225, 15 squared, minus 4 times negative 100 is 400, times 3 is 1200, over 2 times 3 is 6. Okay. At this point, we can simplify a little bit, and then we'll just use a calculator. Negative 15 is plus or minus the square root of 1425 over 6. Calculator time. So we plug that into our calculator. And when we plug this into our calculator, we get two answers. Let's look at them. Our two answers are t equals negative 8 point, we'll round a little, 85 seconds. And the second one is 3.85 seconds. Okay, so we get two answers according to math. Let's think about this. can you have negative time? Does that make any sense? Can you go backwards in time almost 9 seconds before the cars started moving? No. So in physics, we would throw this answer away because it's not possible. First of all, we can't go backwards in time. Second of all, it's kind of nonsensical. Do we know that the cars were even doing that 9 seconds before? Not really. What if we didn't even start the race until 3 seconds before, right? Let the first car get up to speed to the 15 meters per second, something like that. So physics doesn't really go back in time very well. So we throw that away. So our answer is 3.85 seconds-ish. I'm rounding a little bit, but it's okay. Now we're going to take this, and we can just go ahead and plug it into either of these equations to find the final position. I'm going to plug it in here because that one looks a little bit nicer to me. So we're going to do x final equals 3 times 3.85 squared. 3 times 3.85 squared. And we get x final equals 44.4675 meters. We could round this 44.47 meters. So this, in this situation, our two cars are going to collide 44.47 meters from 0. So from this way, right there, 44.47. And it's going to take them about 3.85 seconds to do that. Okay, there we go. So these are the big kid problems. These are like the real nasty ones. I promise not to give you too many of these because they get pretty gross and pretty math heavy. And really, the physics ended a long time ago, right? The physics was reading the question, picking out our variables, identifying the equation we were going to use, and then below this line, math, quadratic formula, bleh, math, physics to put across through this, math. So unfortunately for you, you have either chosen or been coerced by your counselor into a class filled with math that masquerades as science, but lucky for you, you like math, duh. So there's 3 problems, kind of tricky problems. So good luck. If you need help with your homework, and you might get some tricky problems on your homework, so this is a tricky lesson, make sure you ask for help. I mean, try it first, but when you get stuck, don't be scared to ask for help. Until next time, have a great day.